Welcome to this introduction to the design of timber portal frames. In this session, we'll explore the key standards that govern timber structural design, AS/NZS 1170, NZS 3603, and NZS 3604. Let's start with our first material, sawn timber. For visually and machine-graded sawn timber, radiata pine is available in all structural grades, while Douglas fir ranges from MSG 6 through to MSG 12, along with VSG 8. Among these, MSG 8 and VSG 8 are the most commonly used structural grades for both species. Sawn timber is supplied in both wet and dry conditions, typically green for machine-graded and dry for visually graded timber. Standard lengths up to 6 meters are readily available, with anything longer usually needing a custom order. Common sizes include 150 by 50, 200 by 50, 250 by 50, and 300 by 50 millimeters in green timber, and 140 by 45 up to 290 by 45 in dry timber. This table summarizes the structural design properties of sawn timber, including bending strength, tension, compression, shear capacity, and modulus of elasticity for each grade. These values are what engineers use directly when sizing members for a portal frame. Our second material is glulam. Glulam is manufactured by bonding a number of graded kiln-dried laminations together with proven adhesives, creating a homogeneous and highly efficient structural timber product. One of its biggest advantages is the ability to produce members far larger than what's typically available in sawn lumber, usually built up using 45 millimeter laminations. In fact, glulam member sizes are almost limitless. In New Zealand, glulam members up to 2 meters deep have been manufactured. Another major benefit is the ability to produce curved members. Glulam is generally supplied in 3 grades, GL8, GL10, and GL12, and is widely used for portal frame rafters and columns, purlins, girts, mullions, flanges and composite beams, and curved structural members. The third engineered timber product is LVL, or laminated veneer lumber. It's manufactured by laminating thin timber veneers, around 3 to 4 millimeters thick, that are rotary peeled from good quality logs and vertically laminated using adhesives. The grain of all veneers runs in the same longitudinal direction, giving LVL properties similar to sawn timber, but with significantly higher strength. In portal frame buildings, LVL is commonly used for rafters, columns, purlins, girts, mullions, and flanges in composite beams. These two tables compare the structural design properties of glulam and LVL side by side, strength, stiffness, and other design values engineers rely on when selecting the right engineered timber for a given span or load. Before timber goes into a structure, it needs to be treated according to its hazard class. This classification depends on how exposed the timber will be, whether it's fully protected indoors, exposed to weather, or in direct ground contact, and determines the level of preservative treatment required for long-term durability. Timber portal frames are generally classified by 2 things: structure type and building geometry. In terms of structure type, we have gable roofs and mono-sloped or lean-to roofs. In terms of geometry, a building can be either closed, fully enclosed on all sides, or open without full wall cladding. These classifications directly affect how loads are distributed through the frame. Every structure is assigned an importance level under AS/NZS 1170, ranging from 1 to 5. Importance level 1 includes structures like storage sheds where no human life is endangered. Importance level 2 covers residential buildings, the most common category for houses. Importance level 3 includes higher risk buildings such as healthcare facilities, daycare centers, schools, and commercial or industrial buildings. This table shows how failure consequences and design requirements scale up with each importance level. Now let's identify the key members of a timber portal frame. These include the external rafter, internal rafter, and the rafter splice joint where 2 rafter sections connect. The vertical pole supports the frame and transfers load down to the pile foundation with the pile depth and pole embedment shown here. Horizontal purlins support the roof, girts support the walls, and roof bracing along with wall bracing keep the whole structure stable against lateral loads. Here's a second view of the same frame reinforcing these terms. The main rafter and purlins form the roof structure, with roof bracing providing lateral stability. Down the sides, The external rafter connects to the pole, which is supported by the pile foundation. Wall bracing and girts complete the wall framing system. Getting comfortable identifying these members is essential before we move into load calculations. Now let's look at the typical loads a portal frame must resist. Dead load, covered under AS/NZS 1170.1, depends on the materials used, their dimensions, and the structure's overall design. Live load, also under 1170.1, depends on the intended use and occupancy of the building. Snow load under AS/NZS 1170.3 is influenced by importance level, snow region, roof slope, and building geometry. Wind load under AS/NZS 1170.2 depends on importance level, wind region, site location, terrain, and building geometry. And finally, earthquake load depends on the building's location, geometry, importance level, and the seismic zone it sits in. Finally, let's look at connectors. These MyTech connector details show how portal frame members, rafters, beams, and poles are structurally joined together, ensuring load transfers safely and efficiently through every connection point in the frame.